Yes, the recording has started. So, welcome to Operators on Hilbert Space. Today, we're going to be discussing assignment 2. So, this assignment is all about distributions, then self-adjoint operators, and spectrums, and so on and so forth. So, these concepts are really important in physics and especially in quantum mechanics. So in quantum mechanics, we deal with these concepts all the time. And today we're going to be talking about the mathematical foundations of these concepts, and we'll solve some interesting questions from the assignment. So let's first look at the first question of the assignment. Let me copy the question here. So this is the question. So it asks us to define the Dirac delta distribution, and we have to explain why this is not a function, rather an element in the Schwarz distributions. Okay, in order to answer this question, firstly, we have to understand what's a distribution. So, and we have to also understand why something may not be a function, but still it can be a distribution. So what's a distribution basically? So a distribution is something that takes a test function and gives out a real number. So it's some sort of a machine that takes in test functions and it gives out a real number. Real, or it may give out a complex number as well. So what is a test function? Well, a test function is actually a smooth and compact supported function, compactly supported function on the real line. So we denote all these functions like this, like C infinity. So C infinity stands for smooth, and then we write a C as a subscript that denotes compactly supported functions on R. So what does compactly supported mean? Compactly supported means basically like all the functions in this space, they are non-zero in a bounded region only. So apart from that bounded region or apart from that compact region, outside of that compact region, that function is always zero. So for example, if we give an example, let's say, so something like this. So this function right here, the graph we have drawn right here. So this function, this is non-zero only on this bounded region. And outside of this bounded region, the function is zero. Therefore, we can say that this is a compactly supported function. So a compact supported smooth function is called a test function. And what does a distribution do? A distribution basically takes a compactly supported smooth function and gives out a number, a real number, or it may give us a complex number as well. So suppose, so let's suppose T is a distribution. Again, since T is a distribution, that means it takes test functions as input. And as output, what does it give? It gives us a real or a complex number. So, and let's call it phi is a test function. Or in other words, smooth and compactly supported function. All right, then what does T do? T takes in phi and gives out a real number. So in the usual function notation, we may write it like this, T of phi. So T, it takes phi as an input, and this is a complex number, right? But in distribution theory, we use a slightly different notation. We use this notation sometimes. We may use this notation that angular bracket T comma phi, then we close the angular bracket. So this is the notation for this. So what does this notation mean? This notation means that T is a distribution that takes a test function, and in our case, the test function is this phi, and this thing is a complex number. So yeah, now this notation right here, it may look like the notation of inner product, right? So in fact, like we have some how do I say this? Like, we have some motivation of writing it like this. Why do we write it like this? Because let's use a different color. So suppose we take another function f. Suppose f is a function. Well, on f we don't have any other condition. Well, for example, phi has a condition that phi needs to be completely supported. But on f we don't have any condition. Then it's a smooth function. So that means it takes numbers and it gives out numbers as outputs. Right. That means this is not really a distribution as of yet, but we can make it a distribution. How do we make it a distribution? We can make it a distribution like this. Let's say we define this thing as the integral of f of x phi of x dx over minus infinity to plus infinity. So in this way, like f can be turned into a distribution. Right. So yeah, that's why. So well, this thing right here, this integral right here, this looks somewhat of an inner product. So, but it's not. It's not exactly an inner product. It's just we turn a function into a distribution like this, and since it resembles inner product, that's why we use the inner product notation right here. All right. Now, what is the Dirac delta distribution? Well, in physics textbooks, you may see something like this. Physics people may write that the Dirac delta function is something like this. It's 0 on if x is non-zero, and it's infinity if x is 0. So this definition right here, mathematicians do not really like this notation because, well, technically speaking, this thing right here, this is not a function, because a function is supposed to take real numbers as inputs or complex numbers as inputs, and it's supposed to give out numbers as outputs. But this output right here, this is not a number. Therefore, this is an invalid definition. Rather, a distribution is best known by how it acts on test functions. For example, so this notation is not really the correct way to define the Dirac delta distribution. So since the Dirac delta, it's a distribution, that means it takes functions as inputs, right? So suppose it takes the function phi as input. Then how do we define it? We define it like this. We define that if the Dirac delta distribution takes phi as input, it's supposed to give out a number as output. And what's that number? That number is phi of 0. So this is the correct way to think about the Dirac delta distribution. So is everybody clear about the proper rigorous definition of the Dirac delta distribution? So if I reiterate a little, so oftentimes in physics textbooks, you may see like something like this, but this is not the correct way to think about the Dirac delta distribution, because well, what does the distribution do? The distribution basically takes a test function and it gives a real number as output. So this distribution right here, which we are calling the Dirac delta distribution, it takes the test function phi as input. And what does it give? It gives phi of 0 as output. So since phi is a function, so that means phi of 0 is a number. So that means the distribution delta that takes phi as input and it gives phi of 0 as output. So do we have any questions from here? Looks like we have no questions from here, so I guess we can move to the next question from the assignment, which is this. So it says compute the distributional derivative of the Heaviside step function. So let's unpack the things one by one. What is this Heaviside step function? It's the function that is, so suppose, let's say this is my graph and this is the function. The function is basically it's 0 here and it's 1 in this region. So in terms of, if we write it in a mathematical notation, the function is h of x. Well, the Heaviside step function is denoted as h. So, yeah, it's named after someone called Heaviside. So how is it defined? It's the output is 0 if x is less than 0, and the output is 1 if x is greater than 0. So if the input is negative, the output is 0, and if the input is positive, the output is 1. So that's the distribute. So that's the Heaviside step function. But here we are asked to compute the distributional derivative. So what does the distributional derivative mean? Well, in the conventional sense, we can find the derivative of a function, right? But here how do you actually find the derivative of h of x? Well, in the negative region, it's a constant function. So in the negative region, the function has derivative 0, and in the positive region as well, the function has derivative 0. But we are not asked to find the conventional derivative. We are asked to find the distributional derivative. So in order to compute the distributional derivative, what we have to do is that we have to consider this function as a distribution. So how do you do that? So what does a distribution do? So if we consider h to be a distribution, it takes a test function as input, and it's supposed to give a number as output. And how do you define it? Well, we have seen something like this earlier, that a function can be turned into a distribution using this integral. So h of phi is defined like this. The integral from negative infinity to positive infinity of h of x, phi of x dx. Right. Now we know that h is 0 in the negative side and h is 1 in the positive side. Right. So we can use this to simplify the integral. So since h of x is 0 when x is negative, that means in the negative region, h has no contribution basically. And in the positive region, h contributes 1. So we can further simplify this integral as follows. This is equal to the integral of phi of x dx from 0 to infinity. That means we have discarded the negative region. Why have we discarded the negative region? Because in the negative region, this product, h of x times phi of x, that is 0, which is why that does not contribute to the integral. Right. So the definition of h of phi is this integral right here. Now, how do you compute the derivative of a distribution? We can compute the derivative of a function, but we cannot. We don't really know what's the definition of a distributional derivative. So let's define it first. Then we'll move on to find the distributional derivative of the step function. So what is the distributional derivative? Distributional derivative. So for this, we suppose that T is a distribution. So if T is a distribution, that means it takes a test function as input and it gives out a real number or a complex number as output. Right. Now we have to define T prime. What is T prime? We'll call T prime the distributional derivative of T. But how do we define T prime? So T prime is also supposed to be a distribution. So since T prime is a distribution, it also takes a test function as input, right? And it has to give out some real number as output. So we are defining that T prime acting on phi is defined as negative T acting on phi prime. That is the definition of distributional derivative. So again, let's reiterate what I was trying to say. So we have that T is a distribution, and we are defining now T prime. So T prime is also supposed to be a distribution. What does a distribution do? A distribution takes in a test function as input. So T prime also takes in a test function as input, and it will give us a real number as output. And what is that real number? That real number is precisely this. That real number is the negative of T acting on phi prime, right? So now one may ask that like why we are defining it like this. We are defining it like this because like what's the motivation of this? The motivation is something like this. Well, if T or T prime were not distributions, rather functions, then how do you like compute these things? Like for a function, like what is f prime acting on phi? F prime acting on phi would be the integral from negative infinity to positive infinity of f prime of x, phi of x dx. Right? So that is the like definition of f prime acting on phi. Now we can actually do this integral like using integration by parts. So if you do integration by parts, then by integration by parts, you will say that this integral is actually equal to like f f of x phi of x from minus infinity to plus infinity, then negative the integral of f of x phi prime of x dx. So how did we get this? We got this by integration by parts, right? So integration by parts gives us this result right here. Well, maybe I shouldn't have like boxed it right like this. So yeah, let's rather highlight it. So this result right here, this we have got using integration by parts. Now, let us focus on this part. Now, since phi is a test function, so phi is compactly supported. What does compactly supported mean? Compact supported means that it's non-zero only in a finite bounded region. Since it's non-zero in a finite bounded region only, that means at both endpoints, at minus infinity and plus infinity, phi is 0. So therefore, the limit as x goes to plus or minus infinity of phi of x equals to 0. Since this is 0, this term right here, this term is actually equal to 0. Therefore, we can say that f prime acting on phi would be equal to minus the integral from minus infinity to plus infinity f of x phi prime of x dx, which is the same as minus f acting on phi prime. So that's why we are defining the distributional derivative like this. So is everybody clear on this? Do we have any questions? All right. So if we don't have any questions, then let's move forward to computing the distributional derivative of Heaviside step function. So we will be basically using this formula right here. So the distributional derivative of Heaviside step function, so h of x or h, whatever. Again, so that means h prime is supposed to be a distribution. Someone wrote something in the chat. Okay, they said it's clear. Thank you for your feedback. So yeah, now we are gonna compute the distributional derivative of h. So the derivative h prime, this is supposed to be a distribution. That means what does it do? It takes a test function phi as input, right? And what does it give? It gives us a number as output. And what is that number? By the definition we have stated earlier, that number is basically like minus t acting on phi prime. So this is equals to minus h acting on phi prime. What is h acting on phi prime? H acting on phi prime is basically the integral from 0 to infinity of phi prime of x dx. Why is this? Well, we have already talked about this, that h acting on phi will be the integral of phi from 0 to infinity. Why from 0 to infinity? Well, h is in the negative region, h does not contribute anything. And in the positive region, h contributes 1. So like 1 multiplied by phi of x is phi of x, essentially. Therefore, yeah. Therefore, h prime acting on phi will be like this integral right here. Now, okay, how do you compute this integral? Can somebody help me? Well, I'm not very good with integrals, so I need some help from you. It's the integral of a derivative. So we can actually like do this integral very easily, I hope. Yes, exactly. This should be just phi of x. So this is the negative sign should be there. This is just phi of x from 0 to infinity. So keep the minus sign. So this is basically phi of infinity plus phi of 0. That's it. Yes. Now, what is phi of infinity? Well, as we have stated earlier, that phi is a test function, that means it's a compactly supported function. Since it's a compactly supported function, that means at both endpoints, the function is 0. It's non-zero only on a bounded region. That means at the endpoints, it's 0. Therefore, phi of infinity, this is 0. So this is just phi of 0. So now we have got that h prime acting on phi is nothing but phi of 0. Does that look familiar? Well, this is exactly the Dirac delta distribution acting on phi, right? Since h prime acting on phi is equals to the Dirac delta distribution acting on phi, and this is true for every phi, therefore we can say that h prime is actually nothing but the Dirac delta distribution. So the distributional derivative of the Dirac delta distribution is, sorry, the distributional derivative of his Heaviside step function is the Dirac delta. So the distributional derivative of h is the Dirac delta distribution. Is everybody clear on this? All right, so let's talk about the next question then. So here we have an operator. The operator is named T subscript Z. So what does it do? It's from the domain of TZ to the L2 of AB. So we all know what L2 A comma B means. It's basically all the square integrable functions in the open interval A comma B. What does it do? It takes a function, it takes something from the domain. What is the domain? The domain is something like this. It takes a function u from the domain, and the output is minus I u prime. So it's minus I u prime. And what is the domain? The domain is all the u from H1, such that u of B is equals to Z times u of A. And what is H1? H1 is the first Sobolev space, if I'm not mistaken. So, so that's all the absolutely continuous functions, such that their derivative is a square integrable function. So we are given some operator, and now first we have to compute the adjoint of this operator. Do we all know what's the adjoint of an operator? Like, what's the definition of adjoint? So let's first recall the definition of adjoint. So suppose T is an operator on the Hilbert space H. So let's on the Hilbert space H. So since H is a Hilbert space, that means H has the structure of a complete inner product space, right? So let's define the adjoint of T. So that means T is an operator from the domain of T to H. Then the adjoint, what is the adjoint? The adjoint is written T star. That is from some other domain. Let's not fix the domain right now, to H. And this adjoint, this has some special property. What is the special property? The special property is, let's take like let's take two values from the Hilbert space. So the inner product of Tx and Y, this is equal to the inner product of X and T star. So that's the special property of the adjoint. So the adjoint is an operator such that this equality of inner product holds. Right. Is that clear to everyone? So what is the definition of adjoint? All right. So let's now talk about the adjoint of our function T subset, right? So how do you compute the adjoint of T subset? Well, we are going to use this equation right here. So how do you compute this? So suppose we have taken two values or two vectors from the Hilbert space. Let's call them U and V from the Hilbert space. What's our Hilbert space right here? Our Hilbert space is L2A. So L2A. So we have taken two functions in the space of square integrable functions. Now let's use the left-hand side of the equation. The left-hand side is TZUV. So this inner product right here. What is this inner product? This inner product is defined as the integral from A to B. Well, we are working with the our domain is the open interval AB, so that's why the integral is from A to B. And how is the inner product defined? It's TZU, so TZU times the complex conjugate of V, depends. Right. So that is the definition of the inner product in L2 space. In physics literature or in some other literature, you may say that the conjugate is given on the first argument, not the second argument. Well, all the math is actually all the computations remain the same actually. So it doesn't really matter which convention you use. So here I'm preferring to use this convention that in the definition of the inner product, the conjugation is given on only on the second argument, right? So what is TZU? As we know, we are given that TZU is minus IU prime. So this is equals to, well, we can take the minus I outside of the integral. So this is minus I U prime. U prime and the conjugate of, and the integral is from A to B. So this is the integral. So yeah. Now, do we know how to compute this integral? Well, as we will see multiple times today, that today the one integration technique that we'll use the most is integration by parts. So here as well, the integration by parts are going to help us. How? So what's the integral if we use integration by parts? The integration will be something like this. This is equals to, well, minus I, then u v bar from A to B. Then this minus will be plus I, the integral from A to B of u, then v prime conjugate. Right. So am I correct? Yeah, looks like this is the correct one. Yes, looks like this is the integration result after integration by parts. Now, let's simplify this a little. So I'm gonna write it like this: minus I. So what's the term? This is u of A, v of A. Well, no, sorry. First, I have to write u of B. U of B, v of B conjugate minus u of A, v of A conjugate. This and then as for the next term, I'm gonna write the next term a little differently. So let's move this here so that I can write it like this. For the second part, I'm gonna write it like this. This is minus I, the integral from A to B. Sorry, no. It's plus u, then in the complex conjugation, I'm gonna write minus IV prime. Right. Is that clear to everyone? Well, basically, what I have done is that I have written I as the conjugate of minus I, and then I've moved the conjugation over here. Why did we do this? Well, our main motivation of doing this is actually this thing right here. This is nothing but the inner product of U and minus IV prime. This is nothing but the inner product of U and minus IV prime. And as we know, using the equation of adjoints, we can say that this thing right here, the inner product of T is at U comma V, that is supposed to be equals to U comma T is at star V. So we have a similar structure here, the inner product of U and something depending on V. So we can understand that well, yeah, we can understand that probably like tz star v is gonna be minus I v prime, right? Provided that this term is zero. So now we are gonna see when this term is zero. So now like the thing we have to deal with is like when this term is zero. So let's talk about that. So when is UB VB conjugate minus UA VA conjugate uh, zero. So let's so in order to do that, we have to actually look at the domain of TZ. So in the domain, where it, so U is actually coming from the domain. So what is U? U is all the functions in the H1 space such that U of B equals to Z U of A, right? So we can actually use this condition right here. So this is zero if and only if in U of B we can write Z times U of A, then VB complement minus U of A, VA complement is equals to 0. Right. So, and from here, we can cancel out U of A, and then we can do the conjugation once again. Then we can say that this is equivalent to V of B being, so Z bar V of B being equal to V of. So that right here is the domain of TZ star. Oh, sorry, I wanted to highlight actually. That so V is coming from the domain of the adjoint, and V has this condition. So therefore, what is the adjoint? So therefore, the adjoint TZ star V equals to minus I V prime. And where is this true? This is true, this holds for only the functions for which this condition holds. Therefore, the domain of TZ is equals to all the V in the first Sobolev space H1AB such that Z bar V of B equals to V of. So that is the adjoint of TZ star. Is everybody clear? So again, let me show it all together. So what did we do? We basically considered the equation of adjoints. So in the equation of adjoints, we have expanded this term, the inner product of TZU comma V. Then if we do some maths, if we apply integration by parts, we get something like this, that TZU comma V, the inner product of TZU and V is equals to some other term plus the inner product of U and minus I V prime. So from this, we can say that the adjoint is equal to minus I V prime, but only when this part right here is zero. That means, so in the domain of the adjoint, this term will be zero. And how does the adjoint works? The adjoint works like this. So from this equality, we can say that the adjoint is basically this, the TZ star V is equals to minus I V prime. So is that clear? So basically we are like applying integration by parts, and then we are trying to get some mathematical insight from it. So we have done the first question, that compute the adjoint of TZ. Now, the next question says that is TZ self-adjoint? So what is self-adjoint operators? So a self-adjoint operator is something like this. So suppose T is from, let's say, domain of T to our Hilbert space is an operator, and T star is the adjoint of T. So what is T star? T star is also another operator that is from domain of T star to H. Right. Self-adjoint means that, well, as the name suggests, a self-adjoint operator is where these two things, T and T star, are the same. So we'll say T is self-adjoint, or I think in the lectures it uh, um, it's written in shorthand as SA operators. So T is called the self-adjoint operator if T is equals to T star. Now, in order for two operators to be equal, the first thing we need to have is their domains have to be equal. Again, I'm gonna reiterate the point that an operator is self-adjoint if, in the first place, the domains of T and T star are equal. The domains have to be equal. Then, if the domains are equal, then we'll consider like how does the operators work. So what are the conditions? The conditions are, number one, the domain of T has to be equal to domain of T star. And then what is the second one? The second one is that their actions has to be the same. So TV has to be equals to T star V for every V in our Hilbert space. Well, not in the Hilbert space, for every V in the domain of T, which is also equals to the domain of T star. So this is the condition for being a self-adjoint operator. Right. Now, in our case, let's write the operators side by side. What is T? Let's scroll back. T is an operator such that like that maps U to minus I U prime. So T is from domain of, sorry, TZ, the domain of TZ to L2 A comma B, and it takes U in the domain and it maps U to minus I U prime. That's how T works. And what is the domain? Let me write the domain once again. The domain of TZ is all the U in the first Sobolev space such that U of B equals to Z U of A. Maybe I have to make it a little smaller so that it fits. So that was in the definition, right? So that was TZ. And what is TZ star? This is also from domain of TZ star to L2AB. And how does it work? Well, we have seen that it also maps V to minus I V prime. So it also maps V to minus I V prime. So by the looks of it, you may say that, well, it's obvious that TZ is the same as TZ star, or that means the operator is the same as its adjoint, right? Because their actions are the same. Both of them take a function and maps it to minus I times the function's derivative, right? So, but just from this, we cannot conclude that TZ is a self-adjoint operator. Why? Because we don't know whether the domains are same or not. Now, what is the domain of TZ star? So the domain of TZ star, as we have computed earlier, is all the V in H1 such that it was Z bar VB. Yeah. Z bar VB equals to VA. That means their actions are the same, but their domains are slightly different. Why? Because one of them is U of B equals to Z U of A. The other is Z bar V of B equals to V of A. Therefore, it's not always self-adjoint. It will be self-adjoint only for those Z such that these two are the same. Now, when are these two same? These two will be the same set if, so therefore TZ equals to TZ star if and only if, so that's an equivalence statement. If and only if like U of B is equals to Z U of A, Z U of A, and like what is like V of A is Z bar V of B. So these two sets must be equal, and in order for these two sets to be equal, we must have this equals to Z times Z bar U of B. That means if these two sets has to be the same, we must have all the U's are equal to all the V's, and all the V's are equal to all the U's. And the V functions has the property that V of A equals to Z bar V of B. We just use that right here. So U of A equals to Z bar U of A. That's what we have used right here. So from this, we can say that what is Z times Z bar? That's the norm of Z squared, U of B. Canceling out, we get that Z bar mod square is. Therefore, TZ will be a self-adjoint operator if and only if like Z bar square, Z mod square is 1. Or equivalently, like Z lies on the unit circle. Like only in those cases, TZ will be a self-adjoint operator. Otherwise, TZ will not be a self-adjoint operator. So, therefore, TZ is self-adjoint if and only if the modulus of Z equals to 1. Well, modulus square is 1 if and only if the modulus is 1. So that's why I've omitted the square here. So yeah. Is that clear? Do we have any questions? All right. So now we have seen that TZ will be a self-adjoint operator if and only if Z lies on the unit circle. Now, this question has another part. So what's the third part of the question? The third part of the question basically says that find all the eigenvalues of TZ. So eigenvalues of TZ. Let's now find that. Again, what is TZ? TZ is an operator that works like this. It takes the function u, and the output is minus I u prime. Right. Now, if let's say lambda is an eigenvalue, well, we know what an eigenvalue is, right? If lambda is an eigenvalue, then we must have that like TZU is equals to lambda u. That's the eigenvalue equation, right? So that means minus I u prime is equals to lambda u. Then we have to basically solve this equation. How do you solve this equation? We multiply by I, so we get u prime equals to I lambda u. Now this is a differential equation that we all know how to solve, I hope. So how do you solve this differential equation? Can somebody help me? U prime is equals to some constant times u. So what is the solution of this? Yes, the solution is exponential, right? So from this we can say that wait u of x equals to some constant times exponential of I lambda x. Now, how do you find the constant? Well, in order to find the constant, yeah, in order to find the constant, we have to use the boundary conditions. The boundary conditions that are given. What is the boundary condition given? The given boundary condition states that, well, I forgot. It's ub equals to z ua, right? So, u of b equals to z u of a. This boundary condition will help us solve this. So that therefore the constant times e to the power I lambda b equals to z times the constant e to the power I lambda b. Well, we don't, no. My bad. We don't really have to find the value of the constant because the eigenspace can be a one-dimensional span, right? So we don't really have to find the constant, but rather we have to check that whether all the values of lambdas are valid. So from here we can say that z is equal to e to the power I lambda b minus a. Right. So yeah. So therefore from here we can say that, well, now we have to actually yeah, now we have to think about something. So from here we have to now, okay, let me go back. So what are we finding? We are finding all the lambdas or all the eigenvalues of our operator. So we are finding all the values of lambda that are okay or that are valid values or that are valid complex numbers. Notice that uh, we don't have any condition on z. Well, we have found a condition on z that it has to be of norm one, but that condition was for self-adjoint operator. Like here, nobody said that like tz has to be a self-adjoint operator. In the third part, like nobody said that tz is a self-adjoint operator. So z can be any complex number. So if z happens to be zero, then e to the power something is zero. Does that have any solution? No, because the range of the exponential function does not contain zero. Therefore, then there is no eigenvalue. So again, if z is equal to zero, then there does not exist any eigenvalue. Right. And so now we have to focus on the other case. So if z is not equal to zero, then z is equal to e to the power I lambda b minus a. So from here, can we find the value of lambda? So if it were a real equation, we could have done something like this, that we could have taken logarithm on both sides. But complex logarithm is actually pretty difficult to take. So the complex logarithm is actually very difficult to think about because that's not a well-defined function, because like one number may have multiple complex logarithm. So therefore, and well, let me like rephrase what I was trying to say. What I was trying to say is that suppose we want to write z as e to the power something, let's say e to the power of c, for example. Then what is c? C is a complex number such that e to the power of c is 7. So let's actually even write it as x plus iy. So x plus iy, where x and y are real numbers. If that is the case, then how do you write this thing? This thing is actually nothing but e to the power of x times, uh, then this is cos y plus I sine y, something like this. Right. That means from here, we can actually say that e to the power of x is nothing but the modulus of z. And what is y? Y is the argument of z. But the complex argument is not like well defined because it repeats because like one number may have like multiple arguments. So there's something called the principal argument. So the principal argument is written with a capital A in many math texts. And with that, we can add any 2 pi k for k being an integer. So that's how complex logarithm works. Right. So from here, we can say that so z is equals to e to the power, what is x? X is mod z plus I, argument of z plus 2 pi k. So by equating, we can say that the modulus of z plus I times argument of z plus 2 pi k is equals to I lambda b minus. And finally, solving for lambda, we get, I'm just gonna like copy paste this whole thing. Divided by I b minus. So that's all the possible values of lambda. Again, what did we do here? We basically talked about complex logarithm here. And here, the most important point is actually this. Well, from here we can understand that e to the power x is the is what? So since this is equals to z, that means this is actually equals to the modulus of z times like cosine of argument plus I sine of argument, right? But the complex argument is not well defined because like for one complex number we can have multiple arguments, and all the arguments are basically like they are apart the distance of an integral multiple of 2 pi. So basically, let me give an example. Suppose this complex number right here, let's say this is 1 plus I. What is its argument? Well, you may say the argument is pi over 4, but pi over 4 plus 2 pi is also an argument. So argument of 1 plus I is pi over 4, uh, pi over 4 plus 2 pi, pi over 4 plus 4 pi, pi over 4 minus 2 pi, and so on and so forth. Which is why we have added this term plus 2 pi k, where k is any integer. So therefore, like z is equals to the exponential of this thing. And after equating, we can say that this exponential is equals to I lambda b minus a. From here, we can find the values of lambda. So what did we get? We got that these are all the eigenvalues of these. Is that clear? Well, these are eigenvalues if z is not equals to 0, because for z equals to 0, we don't have any eigenvalues. Yeah. So that was a bit of an exploration into complex logarithms and how complex logarithms work. Are we all on the same page about this? Or do we have any questions? All right, so we have talked about the first three questions of the assignment, and we've been talking for about an hour. So let's take a 5 minutes break, then we'll talk about some more questions. Let me pause the recording. Yes, the recording has resumed. So let's now look at the next question. The next question is actually about the Laplacian, whether the Laplacian is symmetric, self-adjoint, or essentially self-adjoint. So yeah, and so the next two questions are actually pretty similar. So let me copy the questions here. Yeah. So yeah. So these questions are actually very similar. The only difference between these two questions are in the domain of the Laplacian. So in the first case, um, the domain is all the compactly supported functions from 0 to 1, right? But however, in the second case, the domain is actually, it's a little complicated. So it's all the smooth functions in the closed interval 0, 1. And we have some boundary condition that A0 U not equal has to be equal to B0 U prime of 0, and A1 U1 has to be equal to minus B1 U prime 1. And yeah, we have some boundary condition. So actually, well, I'm not gonna like solve both the questions. Rather, I'm gonna solve only the second one. The first one should be like essentially the same as the second one. So that's why I'm gonna like do the second one only, and then yeah, you should be able to solve the first one as well. So so let's look at the question. The first question is that is delta symmetric? So in order to solve that, we have to understand what a symmetric operator is. So what is a symmetric operator? So a symmetric operator is actually like somewhat weaker condition than self-adjoint. So suppose T is an operator from domain of T to some Hilbert space H. So T is called symmetric if T U comma V, this inner product is equals to U comma TV. So that is our definition of a symmetric operator. Now, what is the difference of symmetric and self-adjoint? Well, if you remember, the equation for adjoint operator was something like this. The inner product of T, U, and V was equals to the inner product of U and T star V. So this equality suggests that this equality basically suggests that TV and T star V are the same. So basically T and T star are the same operators. But that's not entirely true. What's true is that T and T star are not necessarily same operators because their domains may be different. Although their domains may be different, but their actions are the same. So they act the same way in the common elements of their domain. So this essentially means that, let's say this is domain of T, and this is domain of T star. So in the intersection of their domains, in this intersection, so T and T star are same in this domain, in this part. So this does not necessarily mean that T and T star are the same operator. So this doesn't necessarily mean that T is self-adjoint. Right, which we'll actually see, because here we have to like later comment that whether like delta is a self-adjoint operator or not. And spoiler alert, we will see that delta is not a self-adjoint operator. That we'll see in a moment. Right. All right. So let's do that. So let's first see whether delta is symmetric or not. So delta will be symmetric if this equality holds. So let me go to a new page actually. So part A. What about part A? Delta is symmetric, or the Laplacian is symmetric if delta u comma v, this inner product is equals to u comma delta v. So if this holds, we will say that if this holds, we will say that the delta is a symmetric operator. So let's now look at let's now look at the like left-hand side of this part. So what's the left-hand side? Delta u comma v, this inner product. Again, what is this inner product? I hope we all know what is how this inner product is defined. This is defined as the integral from 0 to 1. Well, why 0 to 1? Because our like Hilbert space is L2 space, and in the L2 space, the inner product is defined as the integral from the left-hand side to the right-hand side from 0 to 1 of delta u times v bar. Now, can somebody tell me what's the Laplacian, or how does the Laplacian work? So what is delta u? So the Laplacian is essentially the second derivative only. Well, we are working only in one dimension, which is why it's only the second derivative. Yes, precisely. So this is u double prime v from 0 to 1. Now, how do you compute this integral? Well, computing this integral, again, we'll take help from our best friend, which is integration by parts. Using integration by parts, we will say that this is equals to u prime v from 0 to 1 minus the integral of u prime, then v bar prime from 0 to 1. Right, so is that correct? Have I made a mistake? I hope not. Yeah. Now, you can solve the second integral as well using integration by parts. How do you solve the second integration? Again, let me copy it. U prime. Wait. I have made one small mistake. Is that I forgot to put the complex conjugation here and here. So u prime v bar from 0 to 1 minus, what will be the next term? The next term will be actually u v prime bar, again from 0 to 1, plus the integration of u v double prime bar from 0 to 1. Have I applied the integration by parts correctly? Yeah, I hope so. Yes. Yeah. So now this thing is u prime v bar minus u v prime bar from 0 to 1 plus what is this integration? We can write this integration as the inner product of u and Laplacian of v, right? Therefore, the Laplacian will be a symmetric. Let me rephrase. The Laplacian will be a symmetric operator if this term right here, let me mark it with red. This red marked term is 0. Let's just now verify whether this term is 0 or not. So let's first write it. So it's u prime 1 v of 1 bar minus u of 1 v prime of 1 bar minus u prime of 0 v of 0 bar plus u of 0 v prime of 0 bar. I hope this is correct. Yeah. So now what are we gonna do? We are gonna essentially apply this condition. What is this condition? What does this condition say? This condition essentially says that, well, uh, it, we have some constants, A0, A1, B0, B1, and so on and so forth. So A0, U of 0 equals to B0, U prime of 0. So we can actually write it as U prime of 0 equals to alpha U of 0. Since these are non-zero numbers, we can actually divide by them. So at 0 we have some boundary condition, and at 1 as well we have some other boundary condition, which is U prime of 1 equals to, let's say, minus beta U of 1. Again, what have we done? We have essentially like divided by minus B1. So we are now going to apply these two equalities here. So basically, why did we do this? We have done this because previously we had four constants, A0, A1, B0, B1. But there are no relationships between those constants. So that's why in order to like reduce the number of like variables we have to deal with, we have done this. So let me now just copy everything here. So let's try to simplify this. What was U prime 1? Well, if we remember correctly, U prime of 1 was what? Minus beta U of 1. So this is minus beta U of 1, then V of 1 bar minus U of 1, and let me see. All right. And what is V prime of 1? V prime of 1 is actually minus beta. So the minus, and this should be plus, and then V of 1. And we have complex boundary. Now, notice that I haven't put the bar over beta, because beta is actually a real number. Since beta is a real number, so beta is actually equal to beta bar. So now you can see that this term actually contributes 0. Now let's talk about the other term as well. So what's the other term? The other term is that minus U prime of 0. What is minus U prime of 0? Minus U prime of 0 is, well, minus U prime of 0 is alpha U of 0, then V of 0 bar, plus U of 0. V prime of 0 is alpha V of 0. We see that everything cancels out everything. So this is all 0. Therefore, finally, the result we get is that the inner product of delta U and V is equal to the inner product of U and delta V. Therefore, delta is symmetric. Is that clear? Do we have any questions about this? Again, here we have got that delta is symmetric only because of the given boundary conditions. Only because the given boundary conditions hold, that actually like helps us to like, keep this term 0, to make this term 0, to make, and if we had a different boundary condition, then we may not have that delta is a symmetric operator. Right. Well, here I think I can give you a hint for the previous question. In the previous question, the Laplacian's domain is actually different. Well, since it's compactly supported, then you can say that it's non-zero only on a bounded portion, or only on a bounded region. Therefore, outside of that boundary region, we have 0. Therefore, the given functions, they vanish at the extreme endpoints, at the endpoint 0 and 1. So that will help you solve 4a. But for 5a, our approach is a little different. Let's use the boundary condition. Is everybody clear on this? All right. Let's now solve problem with part B. What does part B say? Part B asks whether delta is self-adjoint or not. Now we already know that delta u comma v is equals to u comma delta v that we have just proven, and we also know that this is equals to u comma delta star v using the condition of self-adjointness. Therefore, using these two, we can conclude that delta equals to delta star on their common domain. Now, what we need for self-adjointness? Therefore, in order to get self-adjointness, we have to get that their domains are the same. So, therefore, delta is self-adjoint if and only if the domain of delta equals to the domain of delta star. Now, we only know the domain of delta. What is the domain of delta? The domain of delta is, let me copy from above. It's all the smooth functions, all the u in C infinity 0, 1, such that u prime of 0 equals to alpha u of 0, v prime, sorry, u prime of 1 equals to minus theta u of 1. That was the domain of delta. But what is the domain of delta star? So here we are going to say something new, that how do you find the domain of the adjoint of an operator? So let's try to solve it. So how do you compute the domain of the adjoint operator? All right. Here, the thing that's going to be helpful for us is this equation. So we know using the adjoint equation that the inner product of delta u and v equals to the inner product of u and delta star. Right. That means, well, in this equation, v right here, v is in the domain of delta star. So here v is in the domain of delta star. Now, from this, we can actually analyze something. What is our analysis? We are analyzing that v is in domain of delta star if and only if there exists something here. That means this gives us a valid value. So that means v is in domain of delta star if and only if there exists some f in our Hilbert space L2 0, 1 such that delta u comma v equals to u comma f. And this has to be true for all u in domain of delta. Again, what did we just do? We analyzed this equation right here. That means v is in the domain of delta star if and only if this quantity right here, delta star v, that generates a valid output. So therefore, v is in domain of delta star if and only if there exists some f in L2 0, 1 such that delta u, the inner product of delta u comma v is equal to the inner product of u and f. All right. Is everybody clear on this? Okay. Now, what do we do? Now, notice that so let's now talk about this equation. We have already analyzed the left-hand side. The left-hand side is the inner product of delta u and v. But that is equal to the inner product of U and delta V. What is delta V? Delta V is V double prime. So the inner product of U and V double prime is equals to the inner product of U and F. Right. All right. Therefore, we can say that F is equals to V double prime. However, we only know, so what information about V we know? Pretty much nothing. But the only thing we know is that F has to be inside L2. Therefore, every V inside C2 of 0, 1. What is C2? C2 is continuously secondary, continuously twice differentiable. Well, because we are doing second derivative, we are taking C2 right here. So every V in C2, if we take any V from C2, V double prime right here is a continuous function. And a continuous function on a bounded interval 0, 1 is actually square integrable because that's bounded. It's a bounded interval. A continuous function in a bounded interval is also bounded. And since it's a bounded function, it's second integrable. So let me rephrase. So for every V in C2 0, 1, what is V double prime? V double prime is continuous on 0, 1. Therefore, V double prime is bounded. And hence, V double prime is in L2, 0. Therefore, for every second differentiable function, we get such an F. And that F is what? That F is actually the second derivative of V. Therefore, like every twice differentiable function is actually in the domain of delta star. Therefore, the domain of delta star is nothing but C2, 0, 1. So we have seen that the domain of delta star is, well, I have to be careful. The domain of delta star is at least C2, 0, 1. Well, the domain may contain much more elements than C2, 0, 1. But we all know but the thing we know that it contains all the elements of C2. Now, from here, can we say anything? Can we compare domain of delta star versus the domain of delta? Are they the same? Not really. What is the domain of delta? The domain of delta is all the smooth functions based on some condition, some boundary condition. And this is like C2, 0, 1 and more possible. On one hand, we have twice differentiable functions and more. But on the other hand, what do we have? On the other hand, we have smooth functions and that too restricted based on some condition. Now, which one is larger? Can somebody tell me? Is C2 larger or is C infinity larger than C2? Which one of this is larger? Well, C infinity means smooth functions, and that means we can differentiate the functions as many times as we want, right? But for C2, we only need twice differentiable. Therefore, these are not the same. Not only are they not same, this is much larger than the other. That means the domain of the adjoint is larger than the domain of Laplacian. Since the domain is larger, we say that they are not the same operators because their domains are different. Therefore, delta is not self-adjoint. Is that clear? So since their domains are not the same, in fact, the domain of the adjoint operator is much larger. Therefore, delta is not self-adjoint. Right. Again, how did we find the domain of delta star? We use this. A function will be in the domain if and only if there exists some other function f right here. And here we have seen that in place of f, I can basically put v double prime. If I put v double prime right here, this equality holds. Therefore, every function which has continuous second derivative is in the domain of delta star. And since the second derivative is continuous, therefore it's in L2. So this is just a verification step. Therefore, the domain is at least C2. So the domain of delta star or the domain of the adjoint operator is C2 and possibly more. On the other hand, the domain of delta is all the smooth functions. So from here, we can actually conclude that they are not the same operators because their domains are different. So yeah, that was the second part. In the third part is actually very interesting. The third part of the question says that, is delta essentially self-adjoint? So we already know that delta is not self-adjoint, but we have to check whether it's essentially self-adjoint. What does essentially self-adjoint mean? Essentially self-adjoint basically means that suppose T is an operator. Well, I should say T is a symmetric operator. Because if an operator is not symmetric, it can't be self-adjoint. So it's suppose T is a symmetric operator, and now T itself may not be self-adjoint, right? T may not be self-adjoint. However, we can close the domain of T, and we form the closure. We can form the closure of T by closing the domain of T. And if the closure of T happens to be equal to T star, we say T is essentially self-adjoint. Right. So these are the concepts that I'm guessing that were covered in the lectures. Now, how do you actually check that something is essentially self-adjoint? Like checking it from scratch is actually very difficult. Why? Because yeah, because the way the closure is defined or the way the closure is constructed, it's very difficult to work with. That's why we have some theorems. I believe this theorem was discussed in the lectures, but I'm gonna go through it once again. Okay. So what was the theorem? The theorem says that T is essentially self-adjoint if and only if T star plus I and T star minus I are injective. Or in other words, the kernel of T star plus or minus I is 0. So if that happens, then we say that T is essentially self-adjoint. So that means it does not have all the strong properties of a self-adjoint operator. Rather, it has some essential properties or some weaker properties. So we won't go into the proof of this result, but we are gonna use this result to show whether our operator Laplacian is essentially self-adjoint or not. All right, let's start. Okay. So how do we actually like use this? So we use this in context of our given operator. So in our given operator, the delta is essentially self-adjoint if and only if the kernel of delta star plus or minus I is equals to 0. Now, what is kernel? Well, we all know what a kernel is. Kernel is basically the null space. The linear algebra term is the null space. So how does one find the null space? Basically, delta star plus or minus I, v equals to 0. We solve this equation. And after we solve this equation, what do we do? After we solve this equation, we essentially say that like if all these v's are in the kernel. So if this equation has the only solution v equals to 0, because v equals to 0 is a trivial solution of this equation, right? So if this equation has the only solution v equals to 0, then we say that the kernel of delta star plus or minus I equals to 0. So let me rephrase it. Therefore, delta is essentially self-adjoint if and only if the only solution of delta star plus or minus I v equals to 0 is v equals to 0. Like, so far up until this, do we have any questions? No questions. So are we all clear, like why we are doing this? We are doing this because we want to use the theorem that I have stated earlier. And what is kernel? Kernel is basically all the inputs for which the operator gives 0. And kernel being 0 means that the only solution of this equation is v equals to 0. Right? All right. Now let's now solve this equation. Let's now solve delta star plus minus I v equals to 0. So let's now solve this. Delta star plus or minus I acting on v equals to 0. This actually means that delta star v equals to minus plus I. So for plus, this will be minus. For minus, this will be plus. Right? Is that clear? Okay. So what we are gonna be now doing is we are gonna solve one part after the other, because keeping track of the positive and negative signs is actually pretty difficult. Well, not necessarily difficult, but it's like we have to be very careful about this. So let's first solve one by one. So first, solve delta star v equals to IV. Then we'll solve delta star v equals to minus IV. All right. Now, how does delta star work? Remember, we have shown that delta is a symmetric operator. Since delta is a symmetric operator, what do we know? Since delta is a symmetric operator, we know that delta and delta star are the same, but only on their overlapped region, only on their overlapped like only in their overlap domain, only in the overlap of their domain, right? So therefore, we have to solve this thing. V double prime equals to IV. We have to solve this thing. Now, how do you actually solve this? In order to solve this, what we are going to be using is the following. We are going to be taking the inner product of V double prime and V. Where are we taking this? Because this inner product is, what is that? What is this actually? This inner product will be, if V double prime is equal to IV, this inner product will be equals to IV comma V. And what is that? That is I, the inner product of V and V. And that is I times what? The norm of V squared. Right. So we have found that the inner product of V double prime and V is equal to I, then V norm squared. Now let's solve the inner product in another way. What will be the other way? The other way will be using integration by parts. What is integration by parts? This inner product is actually integral from 0 to 1, or yeah. This is the inner product, the integral from 0 to 1 of what? V double prime V, right? And from here, we can actually use integration by parts. Using integration by parts, what do we know? Using integration by parts, we know that this is equal to V prime V from 0 to 1. Wait, I made a mistake. There should be a bar here. Sorry for that. So this is V prime V minus the integral from 0 to 1, V prime bar. And this is nothing but V prime V from 0 to 1 minus the integral of V prime mod square from 0 to 1. Let me write it more clearly. This is V prime bar square. All right. Now let's see one thing. This part right here, what is this? It's a real number. So this observation will come in handy, actually. So this part right here, let me highlight this. This is actually a real number. Now let's talk about the second part as well. What is the second part? The second part is V prime 1, V1 minus V prime 0, V0. Again, I made a mistake, which is I forgot to put a bar here and here and here, and here. Yeah, my bad. But yeah, I have corrected it now, I hope. So yeah. So now using this, we can use the boundary conditions. What are the boundary conditions? This boundary condition says that this is equals to minus beta V of 1. This is V of 1 bar minus alpha V of 0, V of 0 bar. Therefore, we see that after compiling everything, we said the inner product of V double prime and V happens to be equals to this thing minus beta V of 1 mod square minus alpha V of 0 mod square minus V prime mod, the integral of V prime mod square. Finally, we get this. So I hope this is correct, right? Now, the most crucial part of the argument. The crucial part of the argument is this. We have computed this inner product in two different ways. In one of the ways, we have seen that this is equal to I norm of V squared, which is a purely imaginary number. But on the other hand, when we have done this, we have done integration by parts and solved this, we got that it's the sum of three purely real numbers. So this is pure imaginary, and this is a pure real number. How can these two be equal? These two can never be equal if they are non-zero. Therefore, the only way they can be equal is if they are both zeros. And since they are equal, we have to have that V itself is zero, which is what we wanted to show, because like no non-zero functions or no non-zero value in place of V solves this equation. Because we have computed the inner product in two different ways. One of the ways shows us that basically shows us that the inner product is purely imaginary. The other way shows us that the inner product is purely real. Can a number be pure imaginary and pure real at the same time? No. Since they cannot be the same, therefore, what's the conclusion? They can be equal only if they are both zeros. Because all the pure real numbers lie in the x-axis of the complex plane. All the pure imaginary numbers lie in the y-axis of the complex plane. And what is their common point? At the origin only. Therefore, they can be equal only when V is equal to 0. Therefore, this thing right here, the only solution of delta star V equals to IV is V equals to 0. Now, we are not actually we are not done. We have to solve delta star V equals to minus IV, that equation as well. But I hope we all can do it, because that's just a like additional minus sign in front of all the terms. So that should not be a difficulty to solve. And then similarly, the only solution of delta star V equals to minus IV is V equals to 0. Therefore, delta is essentially self-adjoint, and we are done. Is the proof clear to everyone? Like the flow of the proof, how we proceeded? So this is the proof essentially. So again, let me rephrase it, or let me go through it once again. Using the theorem I have stated earlier, we know that like delta is essentially self-adjoint if and only if the only solution of delta star plus or minus I acting on V0 equals to 0 is V equals to 0. So that means there is no non-zero solution of that equation. That we have to show. So now suppose delta star V equals to IV. So then using that information, we have computed the inner product of V double prime and V using two different ways. One of the ways gave us that they are, so that inner product is a imaginary number. The other way using, The other way using integration by parts says us that that inner product is a purely real number. But something, I think, so a quantity cannot be purely real and purely imaginary at the same time. Therefore, the only possibility is when V is equal to 0. Similarly, the other solution also has only the zero solution, only the trivial solution, and hence the delta is essentially self-adjoint. So yeah, we have crossed our time. So unfortunately, we don't have the time to discuss the last two questions. I think we can discuss the questions in a later tutorial or so. But for today, like, is everything clear up until now? Or do we have any questions? All right. So if nobody has any questions, so let's call it a day for now. Thank you everyone for joining. Let me stop the recording.